Hello physics students. Today we're going to be talking about graphing motion. Remember, kinematics is the mathematical or the numerical way to catalog motion. And so what we did is we catalog motion using three ideas: displacement, velocity, and acceleration. Three vectors. And so if you catalog any one of those for an object with either numerical values or with formulas, as we did in the last physics video, then you have captured the motion mathematically. But there's another way, and that we're going to learn today. Of course, in math, you know that you can graph functions. So same thing with motion. You can graph the motion of an object, and from that capture the information about how it's traveling. So three graphs we're going to be looking at: displacement versus time graphs, velocity versus time graph, and acceleration versus time graph for the three kinematic quantities. But we're also going to split our studies into two kinds of motion. One where the object is not accelerating, we would say that's a constant velocity, or Regents likes to use the word uniform velocity. So we're going to look at the three graphs for something moving at a steady pace. And then we're going to look at the three graphs of displacement, velocity, and acceleration for something speeding up, slowing down, or turning. Well, not turning today, but something accelerating. So let's begin. First, I'll step aside and I'll let you jot these notes down. Okay, so the displacement versus time graph for something moving at a constant velocity or uniform velocity, what you have here are straight diagonal lines, either upward or downward. In the case of this green arrow or this green plot, what it represents is something that's beginning at some origin at a x equals 0 along an x-axis, and it moves forward and fast compared to this graph, which starts far away from an origin but slowly comes back to that origin and getting closer to x equals 0. So this was backwards and slow. How do I know that one's fast versus slow? Well, this one covers more distance per time than this one, or displacement versus time. In other words, if you calculate the slope of these lines, you get the velocity. Remember, slope of a function is change in y over change in x. And what we have on the y-axis is not y, but displacement. And what we have on the x-axis is time. So change in y over change in x, d over t, is velocity. Okay? The next set of graphs, that's for displacement. How about for the velocity? The velocity is constant. So how do we draw something that stays constant with time? As time goes on, the graph cannot go up or down straight across lines. So this is representing the forward and fast. In other words, this might be like 10 meters per second, positive 10 above the t-axis. This is backwards and slow. In other words, instead of positive 10, maybe it's down at negative 2. Okay, so that represents backwards and moving more slowly. And finally, the acceleration graphs for both objects, whether you're moving backwards or forwards, fast or slow, your acceleration is 0 if you're not speeding up or slowing down along a straight line path. Okay? So don't get fooled if something's going 100 miles an hour past you, but it's going steady. Acceleration 0, just like the pebble sitting on the beach right in front of you. Not moving, not moving, not moving. Also acceleration 0. So don't confuse velocity and acceleration. Okay, constant velocity, steady pace. Now let's look at the graphs for something that's accelerating. First of all, I want to point out that the Regents will say constant or uniform acceleration. Actually, I'm getting a little ahead of myself. Let me pause and let you copy these notes down. Okay, so why constant acceleration? Well, in real life, acceleration is not always constant. It's seldom constant, really. But that's too complicated. What we're talking about to study in our curriculum, what we're talking about are things that speed up or slow down at the same rate throughout. In other words, your speedometer reading changes by the same increment every second. So for example, maybe you go 0, 2, 4, 6, 8. That's your speedometer reading. So that's an acceleration of 2 meters per second squared. 2 every time, right? Or your speedometer could go 0, 5, 10, 15, 20. I'm adding 5 every time. That's an acceleration of 5. But every time I add 5, I don't add 5 and then 6 and then 7. No, I have a same acceleration throughout. So just keep that in mind. Okay, so here are some graphs. Notice the difference. These are curved compared to those, which are straight lines. Okay, so this first graph, this basic half parabola here, represents something moving forward and speeding up. So first of all, it's starting at an origin at somewhere at maybe an x-axis of 0. And then how can I tell it's moving forward? Well, notice the displacement gets further and further. So it's going to like x equals 1, 2, 3 on upward. So it's definitely moving forward. How can I tell it's speeding up? Well, as before, the slope of a displacement graph is equal to the velocity. And you might say, well, how do we draw a line here? Well, what you have to do is you have to imagine a tangent line. I guess I got my meter stick here. So, if I put this tangent to the curve right here, you see that the meter stick is roughly at 0 slope. That means the car is not really moving. But if I look at it maybe 1 second later, in order to make a tangent line, look what I have to do. I have to tilt this like this. So now, that means that at this point, the slope of the curve of this tangent line is greater than it was over here. It's sped up. And then if I go, say, right here, now I have to make the line here tangent to the curve to figure out the velocity at that point. So there, you notice it's steeper still. So this function is getting steeper and steeper and steeper. This graph means the object's going faster and faster and faster. And if we wanted to calculate the actual velocity at that instant, what we'd have to do is construct a tangent line. So we'd have to draw a line like this, tangent to the curve, and then we would find the slope of that tangent line, delta d over delta t, and that would be the velocity right there where that line is tangent to the curve. That'd be the velocity of the object at that moment. So that's how we tell this is speeding up, because it's getting steeper. Slope is velocity, okay? Yeah, maybe I should have left it. Thought it was cluttering. But the other plot. How can we tell this is moving backwards and that it slows to a stop? First of all, it's starting away from the origin of some kind of x-axis. So maybe it's starting not at 0, but at 50 meters away. And then notice the graph, it's going like 40, 30, 20, so it's coming backwards. So that's how we could tell it's going backwards, returning closer to the origin. How do we tell it's slowing down? Again, if we make a tangent line here, look how steep that is. Maybe that's like a slope of negative, not positive, right? It's a slope of negative, and maybe like negative 20. A little bit later, watch what happens. The slope becomes maybe only like negative 15. Not as steep anymore. How about a little bit later over here? Tangent line, instead of being like this, it's now a less negative slope. Maybe it's like negative 10 instead of negative 15. And then eventually over here, it goes to 0 slope if we do a little tangent line right here. So it stopped right over here. So it was going fast backwards, slow, slower, 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 stopped. Because again, slope is equal to the velocity. All right? So let's move on to the other graphs. I'll pause the video, give you a chance to jot these down. Looks like I bumped into here and erased a little of the axis, okay? Okay, so the velocity graph for this object moving forward and speeding up. It started at 0 velocity. Imagine drawing a tangent line here, right? And then the velocity goes more and more positive. So we start at 0 and go more and more positive because the curve gets more steep over here for velocity. This graph, well, as I said, the slope started at a high negative number, maybe like -20, and then gradually it goes to 0. So the velocity went to 0, okay? Slowed down to a stop. Now, the slope of this graph turns out to be the acceleration. How do we know that? Well, if I calculate the slope here, I do change in y over change in x. Well, what's on the y-axis is not y, but velocity. What's on the x-axis is time. So change in y over change in x is delta v over delta t, which would give you the acceleration. Okay, so slope velocity graph, acceleration. All right, and the last one, if I were to ask students to come up with this on their own, not many would get this right. People, again, think, well, wait a minute, if this object's slowing down, its acceleration has to be negative. Not so. Remember, negative acceleration doesn't always mean an object slowing down. Positive acceleration doesn't always mean an object is speeding up. The key is if you have a positive velocity to slow down, you need a negative acceleration, yes. But if you have a negative velocity, to slow down, you need a positive acceleration, okay? Again, your velocity might be -10, -8, -6, -4. That's a positive change every second to slow down when you're going negative. So slowing down negative, positive acceleration. Another way to think about it, a more foolproof way, is the slope of this line is acceleration. This is a positive slope. How about this one? That also has a positive slope, not a negative slope. It has a positive slope. It's sloping upward. Positive acceleration. Okay? So that's it for today, graphing motion. Again, what you want to be able to do is know the differences clearly. Straight lines for displacement, constant velocity, curves for displacement, accelerating. Okay? Could be a curve like this, like this, like this. Doesn't matter. If it's a curve on the displacement, it's accelerating. Straight line. Velocity graphs for something moving at a steady pace, not accelerating. Horizontal lines, because the speed can't be increasing or decreasing. But for something accelerating, the lines have to be diagonal, either velocity increasing or decreasing, or like this or like that, right? Some kind of diagonal line for velocity instead of straight across. And finally, for acceleration graphs, for something at a constant velocity, it's not accelerating. So whether you're moving fast, slow, forward, backward, doesn't matter. Your acceleration is 0. And then for something accelerating, it's a horizontal line, but not 0 like before, but somewhere above or below the t-axis. So those are the patterns of the graphs. We'll practice more drawing these graphs, interpreting them later in the topic. All right, so I'll see you in the next physics video. That's it for today.